Okay, let's dive into this. Welcome to today's Explainer, where we are going to do something, well, way more exciting than just memorizing a giant list of physics formulas. If you've ever studied linear motion, you've probably had to cram a bunch of equations into your head right before a test, right? But today we are going to look under the hood. We're going to use the beautifully elegant language of calculus to actually unlock these equations and discover exactly where they come from. I really want you to think about that for a second. We tend to treat these equations like universal laws handed down from the sky, governing everything from a falling apple to a speeding rocket. But where do they actually come from? Like, are they just random algebraic guesses? Or is there a fundamental underlying code that perfectly dictates how objects move through space and time? Well, spoiler alert, it is absolutely the latter, and calculus is the key. So here's our roadmap for today. We'll start with the standard kinematic equations, look at the calculus connection, derive the first and second equations step by step, and then finally wrap up with the mathematical big picture. All right, section 1, the standard kinematic equations. Okay, so here is the classic set of variables. You might remember these by the acronym SVAT. S, or x, stands for displacement, basically how far an object has moved from its starting point. U, or v sub 0, is our initial velocity, while v, or v sub f, is the final velocity. A represents acceleration, and t, of course, is time. You can think of these variables as literally the alphabet of our motion language. By combining them, we can describe reality, and this brilliantly illustrates why these variables actually matter in the real world. You see, this isn't just some abstract theory on a chalkboard. What you're looking at here is a top fuel dragster doing a burnout, getting ready to accelerate from rest at a massive average rate of 26.0 meters per second squared. That is wild. To predict exactly where this dragster will be and how fast it'll be going at any given fraction of a second, we absolutely rely on the relationships between those SUVAT variables we just talked about.
Moving right along to section 2, the calculus connection.
Now, in calculus, we understand motion through rates of change. Acceleration isn't just some static number, it's literally defined as the time derivative of velocity. We write that as a equals dv over dt. Similarly, velocity is the time derivative of position, written as v equals dx over dt. Now, if we know that differentiation takes us from position down to velocity, down to acceleration, well then calculus gives us the ultimate reverse engineering tool to go backward, and that is the integral. I absolutely love this quote. It's translated from one of our physics educators who was walking their students through this exact derivation. Let's integrate this thing. I mean, it perfectly captures the exact mindset we need here. We aren't doing calculus as some boring chore. We're using it as an incredibly powerful, exciting tool to unlock the secrets of physics. Now, what's really interesting about this slide is just how simple this core concept really is. Because acceleration is the derivative of velocity, we can just take the indefinite integral of both sides. As you can see, velocity as a function of time, v of t, is equal to the integral of acceleration with respect to time, plus a constant of integration, c1. This right here, this is the seed from which all of our kinematic equations are going to grow. Which brings us to section 3, deriving the first equation. Okay, I'm going to deliberately slow down a bit right here so we can clearly follow the logic together. First, to find a specific equation, we need to set the limits of our integration. At time 0, our initial velocity is u, and at time t, our final velocity is v. Next, we integrate our acceleration, a, with respect to time dt. But wait, here is a massive requirement. For this to work, acceleration must be a constant. Because it's constant, we can pull a right out of the integral. Finally, we just evaluate the upper limit minus the lower limit. The integral of dv from u to v gives us v minus u, and the integral of dt from 0 to t gives us just t. And when we rearrange that simple results, boom, we get this. V equals u plus at. Final velocity equals initial velocity plus acceleration times time. That's the first equation of motion. If you've ever blindly memorized this formula before, take a moment to appreciate this really satisfying aha moment. It's not some random rule. It is the direct, logical consequence of integrating a constant acceleration over time. Let's move to section 4 and see how this builds into deriving the second equation. So we're going to use the exact same logic. We know velocity is the rate of change of position, dx over dt. So we take the equation we literally just derived, velocity equals u plus at, and we substitute it into a whole new integral to find displacement. We integrate the initial velocity term, u, with respect to time, which simply gives us ut. Then we integrate that second term, at. Remember, the integral of t with respect to time is 1/2 t squared, so at becomes 1/2 at squared. We peel back those mathematical layers, and what do we get? We get the classic displacement formula. Displacement, x, equals the initial position, x0, plus initial velocity times time, plus 1/2 acceleration times time squared. Again, pulled right from our university physics source, this perfectly reinforces how initial position, initial velocity, and an accelerating rate of time all seamlessly combine into one unified formula.
Finally, Section 5, the mathematical big picture.
Traditionally, you might have derived these equations using graphs. The algebraic method relies heavily on geometry, stuff like finding the area under a velocity time graph by breaking it into rectangles and triangles, or calculating the area of a trapezoid to find displacement. And hey, it works, but it's kind of clunky. But then we have the calculus method. It's an elegant, direct manipulation. By simply understanding that motion is a series of derivatives, position to velocity, velocity to acceleration, we can use indefinite integrals to effortlessly slide back and forth between them. It's just a much more fluent language to express how things move. So the crucial point is this. First, these beautiful, simple formulas absolutely only work when acceleration is constant. If acceleration changes, well, these exact equations kind of fall apart. Second, integration is literally the ultimate tool to reverse engineer motion. And finally, when you learn physics this way, calculus transforms what used to be agonizing rote memorization into a profound foundational understanding. You aren't just remembering a formula anymore. You actually know the code that builds it.
But I want to leave you with a question to chew on. We just established that these derivations, these incredibly neat and tidy equations, rely strictly on acceleration being completely constant. But think about driving a car in heavy traffic, or a rocket pushing violently through the atmosphere. In the chaotic, dynamic real world, acceleration fluctuates wildly. So what happens to the math then? How do we calculate motion when the rules of the game are constantly changing? Keep that provocative thought in mind as you continue your physics journey. Thanks for joining me on this explainer, and as always, keep exploring.